Hey there, ever wondered about these beautiful visuals? How on earth do these tuned arrows stacked upon one another trace out almost any drawing? In this video, we will try to understand the underlying math as if you and I have no idea about it. Let's begin with some basic math for this video. Iota is the square root of -1 and setting it as the vertical axis with real numbers as horizontal axis, we get the complex plane. On this plane, we can plot any complex number we want. If we draw an arrow to a point, that point can be written as r cos theta plus iota sin theta, where theta is the angle the arrow makes with the positive x-axis. This can also be written as r times e to the power iota theta, where r is the length of the arrow. If the theta is varied, the tip of that arrow traces out a circle. These arrows can also be interpreted as vectors. We begin with simple curves. Suppose we have a shape whose equation is given as t plus iota t squared. If we plot, it's just a quadratic. We then take a wild guess that the function is already made up of many rotating vectors. Precisely, it is made of vectors of all kinds of frequencies. Means v1 is a vector rotating at frequency 1. v minus 2 is a vector rotating at frequency minus 2. Negative frequency means it's just rotating clockwise. So our function becomes sum of vectors having frequency minus infinity to infinity. Let's write in a more concise way. Alright, but how do we write Vn? All we know about a vector is that it's some kind of an arrow which is rotating. So we put some e to the power iota theta terms in it, which will make our Vn rotate. Let us vary theta linearly with time as t. The speed of rotation is determined by its frequency, which we will set to n. As n varies from minus infinity to infinity, we get all sort of frequencies. 2 pi ensures we get full rotations as our time t goes from 0 to 1 second. We then multiply it with some constant which sets the length of the vector, call it Cn. We are almost there, but Cn is unknown. There's a very nice way to find them. But first, let's expand the function to a few terms to see what's going on. Take integral both sides and focus on the C1 integral. As t goes from 0 to 1, the vector rotates a full circle. This integral can be understood as adding infinitely tiny vectors originating from origin in all directions. Each one of the tiny vector has an opposite vector to cancel it out, and hence the final value of entire integral reduces to 0. Same is true for all terms, but the only exception here is C0. Notice that its vector does not rotate at all, and because of this, the integral is equal to C0. We can write a formula for C0, and finding it is as easy as calculating this integral. To derive other constants, we can multiply the entire expression in such a way that vector of that integral stops rotating. For instance, to find C1, we multiply its by conjugate, and doing so, all the other vectors rotate except C1's vector. This means that all the other integrals become 0 except C1. Thus, the general formula for Cn can be given as this. Sorry to spoil, but Cn is not only the length of vector. If we calculate, it turns out to be a complex number. This gives us two critical pieces of information which we overlooked back then. First is obviously the length, and the other one is the starting angle of that vector. Once we have this data for every vector, we are then ready to set our animation. We let the computer calculate the coefficients for us. Practically it is impossible to find infinite number of them, so instead we will calculate only n number of them. We also pass in a function which we need to plot. We then loop through half of the negative and half of the positive frequencies, and for each frequency we calculate the conjugate we need to multiply to make that vector stop rotating. We then multiply it and then take the integral of it from 0 to 1. This will give us the coefficient Cn. We then extract the required information like the amplitude, which is the length of the vector, then the phase, which is the starting angle of each vector, and then we store it in a list and then store that list in another list called data. We do this for all of the frequencies and then finally we just return that list. In our main code, we get the required data by passing n equals 21 and passing in a quadratic function. We then create the vectors out of this data, stack them on one another, and vary the time from 0 to 1. As we increase n, we get much better approximated shape. The plot may look weird at first glance, but take some more time. It really is a quadratic function. That's impressive. But drawing any shape is more impressive. For that, we use SVGs. SVGs are just like PNG, JPEG, but they store the shapes as mathematical curves rather than pixel data. I used Inkscape to draw the SVG, saved the file and loaded it in our code. Then I extracted the points over that SVG file, convert them into complex points, and the rest as usual. The only difference here is that we are not passing in a function now, but instead we are passing a set of complex points. And also we don't take integral. Rather, it's a discrete sum now because we are sampling limited points, unlike plotting curves. Also, you could see that more the number of points, more the time it takes to compute the coefficients. That's why we have something called fast Fourier transform, or FFT in short, but that's a topic for another video.